What I want to do really is temporarily press pause here. I want to try and put everything together here. I have one more lesson called orbital mechanics, but I figured it's better to do that one after spring break as kind of a review after a 2-week gap. So here's what we're going to look at. This was in the homework, but we're going to talk about it. Geosynchronous, I think that's spelled right. There you go. Satellites stay in one place above the Earth while in orbit. A geosynchronous satellite appears to stay, well, it does stay above the same place on the Earth while it's in orbit. So the first question is, what is the period of such a satellite? This one doesn't require any fancy schmancy orbital mechanics. Yeah. 24 hours. Okay, so we can say this. The period is 24 hours, which is going to be 24 times 60 times 60, which is what? Okay, more specific than something or other? Is it 86,400? 400 or 100? 400. Don't use your sheet. Remember, we talked about that there's a difference between what your sheet says, because it's actually talking about how long it takes the Earth to face the sun at this again, but the Earth is moving laterally. Anyways, if we're just talking the spin here, 24 times 60 times 60, 86,400. Okay. So, what is the orbital radius of such a satellite? What does this question want me to find? Got to be more fussy. What kind of a radius? Did you say orbit? Okay. So now we can go, gravity is what's pulling me in a circle. We can say big G, big M, little m over r squared. It's always mass times acceleration. Don't write that down just yet. It's really mass times circular acceleration. Don't write that down just yet. Write the m down. Please don't forget to write the mass, because it's mass times acceleration. But which version am I going to use here? V squared over r? I totally disagree with that. Why? Because what did I find in part A, Connor? Period. Yes? I'm going to use the 4, the pi squared, the r, the over, and the t squared. Robbie, conveniently here, it doesn't matter how big the satellite is. They're all going to be, if they're geosynchronous, they're all going to be at the same radius, which they will be. I think I'm going to multiply the r squared up to there. That's going to give me an r cubed. In fact, I think I'm going to get this. R cubed equals big G, big M, t squared, I think over 4 pi squared. Is that right, Rebecca? I think, yeah. Except, Rebecca, how'd I get rid of a cubed? Oh, boy, I get to use a button I hardly ever use on my calculator. So it's going to be the cube root of 6.67 times 10 to the negative 11. I don't know about you, but I've got all the Aladdin music still running through my head. That's a catch. Those are catchy. Anyways, okay. People on YouTube are, what? 5.98 times 10 to the 24th. 86,400. Don't forget the squared. Divided by 4 pi squared. What do I get? Cube root of that. Where's my cube root button on mine? It's here. Cube root of that. Do you get 42250,474?
Yep.
I'm going to write down this whole answer because I'm going to use this in just a second, and then I'll round off to 3 sig figs. So I'm going to go 42250,474. 42250,474. That's meters. If you want it in kilometers, you could divide by 1,000. So it's really 4.23 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters. So one thing I can do when we're talking about orbital mechanics is I can give you some information, Nikki, the period, the radius, or the speed, and say find one of the other two. That's from a few days ago. Now let's bring in some work. Part C. Suppose we want to put 12,800 kilogram satellite up there. How much work just to lift it to that radius, question mark? Josh, do you see the word orbit at all in part C? Okay, so we're not in orbit, we're just lifting it up there. First, this is calculating how much fuel will we need just to get the satellite there? Well, how much work, how much energy, and then we calculate how much fuel. What does this question want me to find? Really? What does this question want me to find? How much what?
Work.
Yeah, work. Right? Yes, yes. So I can't go force times distance because gravity is changing as we go further and further away. It would be, I could go the area under the curve, except it's a curve, which doesn't help much because I don't know how to find the area of that. So I have to go work equals okay. Right now, Robbie, underline the word lift, and because we're just lifting, we're going to assume the change in kinetic energy is 0. We're not putting it in orbit. In fact, when we let go, it'll come crashing back down to the Earth and explode, smash into the Earth. The next part, part D, will actually figure out how much work to put it into orbit and keep it up there. But for now, okay. What's changing anything? Oh, so I can just go like this, right? MGH final minus MGH initial? No, why can't I? Oh, we're going cosmic. We have to use the cosmic potential energy equation, which is going to be negative big G, big M, little m over R final. I think R final is going to be our answer from part B, minus negative big G, big M, little m, all over R initial. I think R initial is going to be, where is the satellite starting? Surface of the Earth. Yeah. Okay. Okay, this is going to be some typing. Let's write in the numbers. We'll use ditto marks and things to be clever. So work is going to be negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. What did I say the satellite had a mass of? 12,800? Just picking something at random. Fairly big-ish satellite. And our final was 422.5474. 422.5474. Conveniently, I still have this number sitting on my calculators. I'm going to use my answer button. James, what's a minus minus the same as? So plus, and then James, I'm going to go ditto mark, same number, times ditto mark, same number, times ditto mark, same number. Divided by 6.38 times 10 to the 6th. Okay. negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 12,800 divided by, answer button. Let me make sure I type this in very carefully, otherwise I can't use my answer button again. I don't see any typos. Do you get for the first one negative 1.20839 times 10 to the 11th? I'll go 1.2084, negative 1.2084 times 10 to the 11th, plus, so the Earth is going to be almost the same. The initial, I just delete the negative, and instead of answer button, it's going to be 6.38 times 10 to the 6th. My initial is positive 8.0023 times 10 to the 11th. So the amount of work, the amount of energy, the amount of rocket fuel that I'd need to pack just to get it to the right radius will be this number, take away 1.2084 times 10 to the 11th. It's expensive to get them up there because geosynchronous satellites are a long ways off. 6.7939. All right, 6.7939 times 6.7939 times 10 to the 11th, and then I'll go to 3 sig figs. 6.79 times 10 to the 11th joules. There's my answer. Sadly, Riley, this is not enough because this is going to come crashing back down. So part C, we said just how much work to lift it to that radius. Part D, how much work to keep it in a stable orbit. Okay. What do we need to add to keep it into a stable orbit? We've already given it a bunch of potential energy to get it up there. What kind of energy do we need to add now? Kinetic. So if we were doing this from scratch, we would certainly say work is change in potential plus change in kinetic. None of these this time, Drake, would be zero because we're keeping it in orbit. Can't be at rest. We would find the change in potential. Did we just do that in part C, Drake? Then you know what? Let's say the change in potential. What did we get? And I'll carry the extra sig figs. 6.7939 6.7939 times 10 to the 11th joules. Give me 1 second. Pause the video. We need to find, which is going to be kinetic energy final minus kinetic energy initial. We've decided here, Michaela, that we're going to go worst case scenario. We're going to, where are we always launching from? Superman's Fortress of Solitude at the North Pole, so we don't get that extra boost. Max, what's kinetic energy final? What's kinetic energy been really since Physics 11? Yep. A half m, and I guess it'll be V final squared. In fact, instead of V final, I think we can actually say V orb squared. Did they tell me the orbital speed? I've scrolled down. Did I give it to you? No? What kind of speed? Did you say orbital? Okay. Gravity is what's pulling us in a circle. Big G, big M, little m over r squared equals m. Connor, which one am I going to use this time? Because I want to find V. M cancels, and one of the r's cancels. How do I get the V by itself? Square. Hey, wait. Wait. What did you tell me, Max, the equation for kinetic energy is? A half mv what? You know what? Why don't I get the v squared by itself and just put... Why don't I just actually put big G, big M, little m right in for there? Apparently I can. That's kind of... Why not do that and be clever? Save ourselves square rooting and then squaring again later. Why not just skip both? So I'm going to get this. The amount of change in kinetic energy is going to be a half little m, big G, big M over R. That's what V squared is, big G, big M over R. By the way, if I wanted to write this slightly differently, just look up for a second. This is big G, big M, little m over R. What's that? I've seen that equation before. This is potential energy, but positive. Right? Potential energy was negative big G, big M, little m over R. This is potential energy, but positive. And what's going to be in front of everything? A half. Just as a bit of a nerd trivia note, for what it's worth, the amount of kinetic energy you need to stay in orbit just happens to be the same as the amount of potential energy up there divided by 2, but positive. It's just a nice little symmetrical coincidence. I never have really memorized that. It's not that convenient a shortcut. So, it's going to be 0.5, 6.67 times 10 to the negative 11, 12,800 divided by, which are our orbit, which was 422, 50, 47, 4. 422, 50, 47, 4. If you have a graphing calculator, some of you do, and I'm particularly lazy, I'm going to go second function enter, and I'm going to go second function enter twice because conveniently that already gives me the 6.67. That gives me the 5.98. That gives me the 1200. I guess I'm going to divide it by 422,50,474. And I guess I also have to multiply it by a half. So, Julie, if your calculator remembers more than one line, have I gone on a rant about getting a half-decent calculator? I have. If it happens to remember more than one line, you can often find part of this pre-typed and just tweak it. No matter what, if you type it from scratch or you type it in this way, you're going to get the change in kinetic energy of 6.042 times 10 to the 10th. We're quite far away from the Earth, which means we don't need to be moving as fast. Oh, but we had to burn more fuel to get far away from Earth, so it's not a win. We don't come out ahead. We're not done. This question said find how much work. Okay. Work was the change in potential plus the change in kinetic. The change in kinetic we just said was 6.042 times 6.042 times 10 to the 10th. What was the change in potential? I've scrolled down. Do you have it on your paper? 6.7. I thought I carried 5 sig figs. 7939. Nice try there, Chief. Times 10 to the 11th. How much work? Plus 6.7939 times 10 to the 11th, and I get 7.40 times 10 to the 11th if I go to 3 sig figs now. And that's joules of energy. If you told me how many joules per liter I got from my rocket fuel, I could now calculate how many liters of fuel I need. Oh, wait a minute. So here's where it gets tricky. Do those liters of fuel also have mass? Oh, my mass has just changed. Go back and resolve. Oh, that would calculate how much new fuel I needed. Wait a minute, does that extra fuel also have mass? Go back and resolve. This really, if you want to do it accurately, it has a constantly changing rate. Calculus works really well for solving something like this, but we're stuck with what we got. What part was that? D? What else could I ask? Final thing. What's the gravitational field up there? Mr. Duick, what is gravitational field? Well, this is not on your formula sheet. Phone face down, Robbie, so it's not a temptation. Thank you. Yeah, you. Phone face down, so it's not a temptation. Thank you. Robbie, I'd like you to write down gravity equals gravity. What was the physics 11 equation for gravity? Whenever I said get the obvious one, what did we write? mg. Where little g is not just the acceleration due to gravity, it's also the gravitational field strength. What's the universal equation for gravity? Big G, big M, little m over r squared. If you want the universal equation for gravitational field strength, it's sort of hidden in the two different ways that we've written gravity. It's there. See how we got that, Julie? It said gravity equals gravity, and the little m cancels. The equation for gravitational field strength anywhere in the universe is big G, big M over r squared. So up where we are in geostationary orbit, the gravitational field strength is going to be 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, divided by what was it? Maybe I have it here. 422,50474. 422,50474. I know the answer is going to be less than 9.8. I'm curious how small it is. I've never done this one before. I did something total. Oh, squared, Mr. Duick. Squared. I can't believe I did that. Squared, Mr. Duick. Squared. Sheesh. Not quite zero, but certainly there, not that big. We're nearly out of the Earth's gravitational well. You guys get 0.22? 0.223? 0.223 what? Units. You could treat it as an acceleration and call it meters per second squared. You could also treat it as a gravitational field strength, which is newtons per kilogram, because acceleration is force divided by mass as well. I like that one because that works more with gravitational force on every kilogram of mass. So I kind of like that unit better, but I'd take both. I hope that kind of roughed off some edges, and this is kind of what we can do. Pause the video for a second.